the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is really kind of the first step into linear algebra after all the review stuff that we've gone through. So this video starts echelon forms, and then after this, there's another video on pivot positions and pivots themselves. And then there's another video on row reduction algorithm, and then solutions to linear systems. It's a lot of stuff to take in, but we'll take it in little bite-sized chunks here. Echelon forms, what the heck are they? Well, as I've written here, it's important to note that all the material in this subsection concerns only matrices. The matrices do not actually need to be the augmented matrices of linear systems. Actually, whenever I say an augmented matrix, it is assumed that that is for a linear system. So if I just say these don't have to be concerned with augmented matrices, you can then assume I mean that there is some type of linear system in the background for that. But anyhow, the conversation in this video that we're going to have is not really concerned with augmented matrices. Of course, it applies to augmented matrices, but it also applies to just matrices in general. The first thing we're going to talk about is the leading entry. And the leading entry is a row by row decision. So every row, almost I should say, every row has a leading entry. And so by definition, the leading entry of a row is the leftmost non-zero entry in that row. And this is why I say that almost every row in a matrix can have a leading entry, but not all rows will have leading entries all the time. And the reason why is that any row of a matrix that only has zeros does not have a leading entry. Take, for example, this matrix right here. If you look at each row, and by the way, you should write matrices row by row. It's just a good habit. It's a little bit easier to not make mistakes if you write row by row. Anyhow, reading this first row from left to right, the leftmost non-zero element is this guy right here. And so that highlighted entry is the leading entry for that row. The next row, well, we have a couple zeros. So the first entry and the second entry are zeros, but third entry right here, that's non-zero. So therefore that's the leading entry in the second row. Obviously this would be the leading entry in the third row. And then the fourth row, because it has all zeros, there's no candidate for a leading entry. So there's no leading entry in the fourth row. I hope that makes sense. Not a big deal. And that's actually why I kind of shove these topics into videos, is because it takes time in class that really people would be bored out of their minds just watching me talk about this when they can get it very quickly in a video. Now that we have the leading entry out of the way, and sometimes I'll slip up and call that the leading term. That's just a habit from teaching algebra for years, but leading entry is really what it would be called in a matrix. But now that we have that out of the way, we can start talking about the echelon form of a matrix, or sometimes it's called the row echelon form of a matrix. So a rectangular matrix is an echelon form, or row echelon form, same thing, if it has the following three properties. The first property, all of the rows only containing zeros are below all non-zero rows. I wrote this matrix below in red because it is not an echelon form for a couple reasons, but the main reason, because of what we just highlighted, is that we have a row of zeros, and yet that row of zeros is not below all non-zero rows. If I wanted it to be written in echelon form, I would at least have to move that row down to the third row, basically swapping rows 2 and 3. And by the way, I'm going to write echelon form over and over again. And like I said earlier, it's known as row echelon form as well. And a lot of us write it this way. That means it's not in row echelon form. So if you see this REF, it means row echelon form. It does not mean some referee in a soccer game or something like that, or football if you happen to be outside of the US. The second property that's a requirement for a matrix to be in row echelon form is that each leading entry of a row is in a column to the right of the leading entry of the row above it. Now, this is hard for people to understand if you read it out loud, so let me go ahead and just showcase what I mean by that. I'm stealing some of the content from the previous matrix, but I'm just making things up here, so let's go ahead and just do this. Notice that in each row, we have a leading entry. The first non-zero entry, starting at the left and moving to the right, you highlight the first non-zero entry, and that is the leading entry in that row. And note, each leading entry of a row, I'm just reading right here, by the way, each leading entry of a row is in a column to the right of the leading entry of the row above it. For example, this leading entry right here is actually to the right of the leading entry of the row above it. This leading entry right here is actually to the right of the leading entry of the row above it. It does not have to be directly to the right. So that's just something that you need to know. It's not a requirement that it's down and over one step. As long as it's down and over, that's fine. So as long as it goes down and then moves to the right to get to the next leading entry, that's perfectly fine. It could go 1, 2, 3 steps. That's okay. So far, actually, this matrix that you're looking at right here, I don't have any zero rows. So 1 is satisfied vacuously. Each leading entry of all the rows just basically steps to the right of the previous leading entry, so that's satisfied. And then the final condition for a matrix to be in echelon form or row echelon form is that all entries in a column below a leading entry must be 0. And out of habit, that's what I kind of did here. So if you take a look at, for example, all the entries below this leading entry, well, that entry below that leading entry is 0, and so is this one. So it satisfies number 3, that third condition. And this leading entry, notice the number below that is 0. So again, that satisfies this third condition. Essentially what you want in the long run is to have a matrix of the form like this, where the asterisks are just some numbers, they don't actually matter, and the blocks are the leading entries in each row. So we have a leading entry in this first row, a leading entry in the second row, and notice any row full of zeros is shoved to the bottom of that matrix. So that satisfies the first condition, that all 0 rows are at the bottom. The second condition is that each leading entry of a row is in a column to the right of the leading entry above it. And that's exactly what you see right here. Let me zoom in. And then finally, our third condition, all entries in a column that are below a leading entry must be 0. So again, here's a leading entry, and notice everything below it is 0. Here's a leading entry right here, and notice everything below it is 0. So this matrix would be in row echelon form. And something to be aware of, a matrix that's in row echelon form is called an echelon matrix. And in fact, I think I have that as a definition. There you go. That's the definition right there. So if I say I have an echelon matrix, it is by definition already in row echelon form. It's got that format that we've just talked about. Little bit of an aside here. The word echelon means step-like. And if you think about the row echelon form of this matrix right here, it is like you have steps. You have this step right here and then the next step over. That's exactly what a row echelon form matrix, or basically an echelon matrix, looks like. It's a step-like matrix. You can see it actually very nicely in this one right here. Step over, step over. Anyhow, that word echelon means step-like, which we will witness in the following examples, and we've already actually witnessed in the examples that I've given. The leading entries of the rows form a staggered diagonal, falling from left to right in a matrix in echelon form. And I call it a staggered diagonal. You probably won't find it elsewhere, but I call it that because these leading entries need not be directly below and to the right of the entry above. A lot of students, when they first learn about echelon form or echelon matrices, believe that they have to look like this. But that's not a requirement to have the steps all nicely staggered like this. In fact, there's an infinite number of matrices that are in echelon form, or basically that are echelon matrices, that don't satisfy that nice step-like pattern where it's single steps, they take double steps and stuff like that. And those are more interesting situations for this course. So far we've talked about leading entries and we've talked about the echelon form of a matrix. And if we have a matrix in echelon form, we call it an echelon matrix. All that sounds pretty nice so far. One little process piece here I just wanted to define, and this is something I was thinking about actually when I was writing or cleaning up, I guess, my lecture notes, is that when you're first entering a course, especially a high-level course like linear algebra, there is a chunk of definitions right from the get-go. Right out the gate, you have a lot of definitions that kind of hit you. And the reason why is because you have to all agree to speak the same language in the course. And in linear algebra, language is critical. You cannot use a phrase or a term loosely in linear algebra because there are hidden meanings behind the way we define things in mathematics. So you have to be very aware of that. Make a list of all the definitions that you're learning in your linear algebra class and just keep that on a sheet or two of paper in your notebook. It's a good piece of advice. Anyhow, let's define row reduction. So the process of applying elementary row operations, I'm going to highlight that. The process of applying elementary row operations to the rows of a non-zero matrix to arrive at a row equivalent matrix is known as row reduction. Before I read the next paragraph, I just want to remind you, the elementary row operations we learned in a previous video. Those are the ones that say, there are three of them, they're the ones that say that the solutions to a linear system are invariant under these three row operations. You can swap rows, which is called interchanging rows in the text that I use. You can multiply a row by a non-zero constant, which is called scaling a row in the textbook that I use. And you can add a multiple of one row to another row. And that is called row replacement in the textbook I use, although I call that the kill step. So those are the elementary row operations, and they can be applied to more than just a linear system. They can actually be applied to a matrix. And if you're watching my video series and you're not a student of mine, you might be wondering where this was introduced. Where did he define that? I define that in the classroom for my students because that's a deeper conversation. But just to quickly define what row equivalent matrices are, two matrices are row equivalent if you can take one and arrive at the other just using elementary row operations. So I have a matrix A and I have some matrix B, and I start applying some elementary row operations to A, and eventually it turns into B. Then we would call those two matrices row equivalent. So having said that out loud, let's go ahead and reread this definition. The process of applying elementary row operations to a non-zero matrix, which is also basically creating a row equivalent matrix, is known as row reduction. So every time that you apply elementary row operations to a matrix, you're basically doing what we call row reducing. Strangely enough, this definition holds whether or not the actual brand new row reduced matrix is reduced in any mathematical sense. For example, its entries might be smaller after you've row reduced it, or they could be larger, or your entries could have been fractions originally, but now they're not. Or it could be the other way around. Maybe originally the entries of your matrix were integers and you just decided to multiply each row by a non-zero constant, 1/7, to get fractions everywhere. Even though that's actually a more complex looking matrix, we would still say you have applied row reduction to arrive at that matrix. And this is where I make my little phrase in here. I suppose the phrase row modified would have been a better choice, but nobody voted for that one at the math meeting that I attended. Now, we've already talked about echelon forms, like what makes a matrix have an echelon form. And we've talked about an echelon matrix. But what if you do row reduction techniques with a non-echelon form matrix to turn it into an echelon form? Well, that's what this definition is all about. If a matrix A is row equivalent, in other words, you did some row operations on it and turned it into a brand new matrix, but this brand new matrix is an echelon matrix. In other words, it satisfies those three conditions. All zero rows are at the bottom, all leading entries staggered to the right diagonally, and any column that contains a leading entry has zeros below the leading entry. So if a matrix is row reduced down to a echelon matrix, we call that new matrix, the echelon matrix you arrived at, an echelon form of the original matrix. Basically, it's like a relative of the original matrix. They're highly related, in fact, almost twins, but they don't look the same. And you'll see that in examples as I move forward, that you can arrive at an echelon form of an original matrix that does not look anything like the original matrix. And reducing to an echelon form of a matrix is an interesting process because there are multiple representations of the echelon form of a matrix. So I'm just going to make up a matrix right now. And I kind of lied there. I didn't make that up. I stole it from an example that we're going to see in a little bit. But might as well just talk about this one here. So we're going to row reduce this and arrive at an echelon form. Well, row reducing this means that we're going to apply elementary row operations, and we want to arrive at an echelon form. So our first step is to use leading entries to kill off entries in the same column but below that. So I want that 4 and that 8 to be 0. Then I'd have a leading entry here and there would be zeros underneath it. And I'd be well on my way to getting an echelon form of this matrix. So to do this, I'm going to keep very close track of all my work, carefully writing things out. And the way I recommend doing this, and I have at the end of my lecture videos somewhere, I give you a suggested kind of list of tactics on how to be very careful with what you're doing. But the main thing is, don't perform two completely different row operations at the same time. In other words, don't do a row interchange and a row replacement simultaneously. But you are more than welcome to do multiple row replacements at once, as long as they're replacing in the same column. As long as the point is that you're killing things off in the same column, you could do multiple row replacements in the same step. So I will take the opposite of 4 times row 1 and add it to row 2 to become my new row 2. And I'll take the opposite of 8 times row 1, add it to row 3 to become my new row 3. So let's go ahead and do this. Now, barring any mistakes on my part, that looks pretty good. Notice we have a lead entry in that very first row, and we have zeros below that. So pretty good so far. I can see I have a lead entry in my second row now. And so what I'm going to do is use that lead entry to kill off what's below. So let's go ahead, and in this case, I'm going to multiply row 2 by 3, negative 3 in fact, and add it to row 3 to become the new row 3. Now this brings up a point that I should be driving home here. Notice that I didn't say in this first step here from this matrix to the next row equivalent matrix to the right there. Notice I didn't say multiply row 1 by 4 and subtract off row 2. You want to avoid speaking about subtraction when you're doing row replacements. Even though it's the same exact action, subtraction mentally leads to a lot of mistakes. So it's better to add negatives to positives than to say, I'll take this and subtract that. Just like in this case right here, I want to use that -3 to kill off the -9. I need that -3 to be positive, because positive 9 plus a -9 will be 0. So I forced that to be a positive 9 by multiplying by -3, and then I added that -9. Notice all of my operations here are addition. Just try to do everything in terms of addition. It's a lot cleaner. Anyhow, let me go ahead and do that now. All right, and we got down to this point. Notice we have a lead entry here, zeros below it, a lead entry here, leading entry there, and there's zeros below it, and then we have another leading entry, and there's no rows below it. So this is now in row echelon form. That is one row echelon form of that original matrix. However, if I multiply row 3 by a -1, I arrive at yet another row echelon form, completely different looking matrix. They are the same. Well, they're not the same. Actually, those two matrices are not the same. They're row equivalent, but they're not the same matrices. However, notice the original matrix, which I could call A if I really wanted to. Let's go ahead and call this A. That original matrix A has two row echelon forms, or two echelon forms. But actually, it has more than that. What if I wanted to multiply row 2 by, I don't care, let's say a -2. Notice those three matrices do not look identical, so they're not the same matrices. However, they are row equivalent because all I did was use a row operation to move between them. But these are all in echelon form. These are all row echelon forms of the matrix A. And this brings us to a very important point about the echelon forms of a matrix. A non-zero matrix can be row reduced via elementary row operations into an infinite number of echelon forms. The proof is incredibly easy because all you're doing is you're starting with a matrix A, you're row reducing until you get to a matrix U, and then you can multiply any non-zero row, or let's say one of the non-zero rows, by any real number other than 0, and you get another version of a row echelon form matrix. That's why there are an infinite number of echelon forms for a given matrix, as long as the matrix has an echelon form. That is, it's not a zero matrix. It's not just a matrix full of zeros. Now that theorem is not as important as a few others, and you'll note as we go through our lectures here, I have certain theorems that will be numbered. The theorems that are numbered are very important. They pop up all the time in linear algebra. So if you see a numbered theorem, take note. Now to continue our conversation about echelon forms, we go one step deeper into the world of echelons, and we get to reduced echelon form, which most people call reduced row echelon form. Some people call it row reduced echelon form. That kind of means the same thing, but the shorthand that we're going to use is RREF, reduced row echelon form. So a matrix is in reduced echelon form, or reduced row echelon form, if it's already in echelon form. So in other words, any row full of zeros is at the bottom of the matrix. The leading entries are staggered from left to right, top to bottom, and all entries below a leading entry must be 0. Those three conditions are satisfied. The extra two conditions that we're about to mention make it a reduced row echelon form. All leading entries are 1, which is kind of cool, and each leading entry is the only non-zero entry in its column. That is, there are zeros not only below the leading entry, but also above it. That matrix is in reduced row echelon form. First of all, it doesn't have a row of zeros, but if it did, I would have thrown it on at the bottom. Second, all leading entries are 1. And finally, in any column that has a leading entry, every other entry other than the leading entry is 0. There is a significant amount of power to be had if you have a matrix in reduced row echelon form. Now, I do want to say this, it's kind of important to mention. Matrices in general can be put in reduced row echelon form. However, you normally don't do it unless that matrix is an augmented matrix. That is, as I mentioned earlier, whenever I say augmented matrix, that is, it represents a linear system. That's really when you want to put a matrix in row reduced echelon form or reduced row echelon form. And just like we had a definition for an echelon matrix, basically a matrix that was in echelon form, we have the reduced echelon matrix definition. The reduced echelon matrix is just a matrix in reduced row echelon form. That's all. And we get to a theorem that has a number. Theorem number 1. The uniqueness of the reduced echelon form. So this is an important theorem. It gets used in proofs, so it's that important. Each matrix is row equivalent to one and only one reduced echelon matrix. So this is significantly different than the echelon matrix. Remember, a non-zero matrix has an infinite number of echelon forms. In other words, you can row reduce it to an infinite number of echelon forms. However, there's only one unique reduced row echelon form of a matrix. So going back to the example I had earlier, if there was some matrix A that we manipulated to get to this being a reduced row echelon matrix, there is no other reduced echelon matrix or reduced echelon form for that original matrix. That original matrix, if somebody said, I need to get to a reduced row echelon form, 1,000 people trying to attempt that would all arrive at this one reduced echelon form, because the reduced echelon form of a matrix is unique. Now, as I mentioned here, the proof of this theorem requires material we will learn later in the course, and we might come back and actually prove this when we have that material on hand. The last thing in this video is really kind of a quick wrap up, basically, the reduced echelon form of a matrix A. Remember that I said it earlier, you have echelon forms for a matrix A. So I give you a matrix A, you can find 1,000 different echelon forms for that matrix A, as long as A was non-zero. In this case, if a matrix A is row equivalent to a reduced row echelon matrix U, then we call U the reduced echelon form of A. That's because U is going to be unique. That's what I just was harping about a moment ago, that each matrix has one and only one reduced echelon form. So anyway, but this is the language for it. So if you arrive at the reduced echelon form for a matrix, you could say, oh, this is the reduced echelon form for that matrix A. Now we're all speaking the same language. Now I get it that this video and a lot of these videos are definition heavy. If you're one of my students, just know that in our classroom, we will spend a great deal of time on theory and really understanding how to use these nuts and bolts. I'm just telling you this is a nut and that's a bolt. But when we get to class, we're going to learn how to use these in very strong theoretical ways. All right, I hope you learned something from this video, and I hope to see you next time in another video or in class. Have a wonderful day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.